everyone. This is Professor Jeff Wilkerson at Luther College with a brief introduction to Exercise 13 from Astronomers as Observers and Experimenters, published by Kendall Hunt. This particular exercise, this activity, is about determining the duration of the sidereal day. And I want to encourage you right now to go look at Project 1 at the back of the laboratory manual, at the back of the book, because that's also about determining the duration of the sidereal day. The difference is there we're looking at stars in the sky and treating it as a project that we carry out over the course of several days or a few weeks, and trying to measure the positions of objects in the sky, whereas in exercise 13 we have some long exposure photographs recorded for you to look at the motion of stars near the pole. All of this, I'll just try to reproduce the figure in Project 1. Those of you who have a keen eye will realize the figure comes from something just like this, standing here to say, if this is the sun and the Earth is here, and you could build a monument to the sun that is an arrow, a big monument, that points directly at the sun. When the Earth rotates around here, the Earth has completed one rotation, so the Earth's going around in this direction, and it comes back, and that arrow's pointed directly toward the top of the board again. It's not pointed at the sun anymore because we've moved this distance in our orbit. That's about a degree. We go 360 degrees in 365 days. We speed up a little bit, we slow down a little bit, but that's the idea, is that we move about a degree in one day. And so we're going to have to over-rotate by about a degree to get the sun back directly overhead again. Now the stars, are so far away that they move very, very little as we move from here to here. So if this arrow was pointed at a star that's way back here, this arrow is also pointed at that star. It doesn't look like it's pointed at that star because this is really, really close compared to the nearest star. That star is actually way the heck up there, so that you can't tell the difference between that and that. They're pointed at the same, at this star again. So when a star gets back to the same point in the sky, it doesn't matter that we've moved this extra degree in our orbit, and that is the duration of the sidereal day, is the time it takes for the star to get back to that point in the sky. It is the rotational period of the Earth. So the object here is to see with what level of precision, how good a job can we do measuring the rotational period of the Earth, the time it takes for a star to get back into the sky. So you've got we got this diagram in the lab book that you can look at to measure those star trails and see these stars moving near the pole. So near the pole is a great place to do this, where you've got the stars. The North Star isn't exactly on the North Celestial Pole, so it moves a little bit, but it's pretty stationary, and you see the other stars making arcs. If you watch for a full day, so we're asking the question, how long does it take for this to get back around to form a full circle, these star trails? So what is that time right there? And that's what you're trying to figure out based on what fraction of a circle those stars made in the time that exposure was that you have in the lab book. So you take that and you say, well, okay, if the exposure was 1 hour, then we can figure out how far the stars went in 1 hour, and we can ask the question, how many hours would it take to go all the way around? If in 1 hour they went 60 degrees, if that angle is 60 degrees in 1 hour, then to go 360 degrees is going to take 6 hours. Okay? So it would take 6 hours to get all the way around, and we'd say the duration of the sidereal day is 6 hours. We can do a lot better than that. We can really get a few digits of precision, and we can even do better than that if we watch stars on the sky, as in Project 1, over the course of 10 days, or 15 days, or 20 days. We might be able to really get the duration of the sidereal day down pretty well. So that's really what this is all about. And you can try different techniques depending on what tools you have available to figure out what that arc length is there, what that angle is right there. You can try various things and see what answers you get. And I encourage you to do that. So to try one technique or another technique in order to measure the duration of, I didn't get that dot very close to the center of that circle at all, did I? to measure the duration of the sidereal day. So you might try various strings, you might try tracing paper, you might try map readers, I don't know, all kinds of things to get an arc length and relate that arc length to this. You just, you're on your own to develop this procedure and to think about this. This is one of the exercises in the book that we didn't give you as much detail of procedure as we do in others. So we walk back and forth this way because that's the astronomer's job, is to figure out what technique is best and then try to apply that technique. And there may not be a best technique. What technique will work to do what we want to do with the level of precision? Once you develop that technique and you measure it, don't trust it. So try a different technique and see if you get the same result or a different result or results that are consistent within our uncertainties of one another and how this goes. And then try another technique and try another technique and really do the best job you can of figuring this thing out. And so, we'll figure out, sort of implied in this little bit of arithmetic that we did was this idea. One of the things that you can do is you can determine if this went 60 degrees in 6 hours, as we said right there. This is anywhere close to the real numbers, but I'm just giving you sample calculations. 60 degrees in 6 hours, then it says the rate of motion, the angular speed of the stars across the sky, is 10 degrees per hour. That's going to be the angular speed of rotation of the Earth. So we can say how long, if it's 10 degrees per 1 hour, we can ask how long does it take to go 360 degrees, right? So 360 degrees divided by 10 degrees per hour is equal to 36. 60 degrees is, oh, good grief. We said 1 hour. Oh my goodness. Let's do it the other way. Let's just do it with let's say it was 6 hours to go 60 degrees. Then it's going to be 10 degrees per hour. A little bit, so we take the 60 divided by 6, it gives us 10 degrees per hour. 360 degrees divided by 10 degrees per hour is going to say, if we're going 10 degrees per hour, it's going to take us 36 hours to get that full rotation. So we can actually, if we want to do that, we can say one rotation per 360 degrees, or 360 degrees per one rotation is probably a better way to think about that. And then we have 36 hours per rotation. So, we stumbled our way through that just a little bit without having it planned out too far in advance. But to say 60 degrees in 6 hours as opposed to the 1 hour that we did over here, just a different example, is 10 degrees per hour. That's the rotational rate. If we take the 360 degrees per rotation and divide by 10 degrees per hour, then the degrees cancel out. The hours that's on the bottom comes up on the top, and we end up with 36 hours per rotation, and that's our duration of the sidereal day. Again, I think you can do better than that. I think you can get 2 or 3 decimal places maybe, and you should try a few different techniques to figure out what that rotational rate is. You don't have to do that calculation that formally. I just wanted to show you how that slightly more formal calculation would work. But the concept here is to say, just by watching how fast the stars are moving across the sky, we can determine, we know what's causing that. It's causing the rotation of the Earth is causing that. And we can determine how fast the Earth is rotating just by looking at how fast these stars are moving across the sky. Different ways to try to do that, and you can play with that in this exercise and play with that in the project. So this is a good thing for you to do. Good luck with the work, everyone. We'll have more for you on other exercises.